Unit 4 Bearing Capacity. The two basic requirements of a foundation are it must not fail in shear and it must not settle beyond the tolerable settlement. So the pressure which the soil can safely withstand both the shear failure and excessive settlement is known as the allowable bearing pressure, represented with symbol QA. There are some terms related to bearing capacity of soil. In that first one is ultimate bearing capacity, represented with symbol QF or QU. It is the gross bearing pressure at which the soil fails in shear. And the second definition is net ultimate bearing capacity, represented with symbol QNF or QNU. It is the net pressure at which the soil fails in shear. So this pressure is obtained by deducting the effective overburden pressure from the ultimate bearing capacity. Then the third definition is net safe bearing capacity, represented with symbol QNS. It is the net pressure which can be safely applied to the soil considering only the shear failure, which is equal to net ultimate bearing capacity divided by factor of safety. Then safe bearing capacity, it is the maximum pressure which the soil can carry without the risk of shear failure irrespective of settlement considerations. So which is equal to net safe bearing capacity plus initial effective overburden pressure. So all these four terms are related to shear failure criteria only. Then the other definition is net safe bearing pressure, also called as safe bearing pressure, which is the net bearing pressure the soil can carry without exceeding the allowable settlement. So it is represented with symbol Q set. Now allowable bearing pressure, it is the maximum pressure which gives safety with respect to shear failure as well as excessive settlement. This can be taken as smaller of QNS and Q set. Types of bearing capacity failures. There are three types of bearing capacity failures: general shear failure, local shear failure and punching shear failure. The first one is general shear failure. So this kind of failure occurs in dense sand and stiff clays. So here if we consider any strip footing which is located on the dense sand or stiff clay, then continuous failure surfaces develop between the edges of the footing and ground surface. So this kind of failure is called general shear failure. So here there is a considerable bulging of soil adjacent to the footing, and here the failure is sudden accompanied by tilting of footing. So here ultimate bearing capacity is well defined. This type of failure occurs when the phi value is greater than 36 degrees, or when the density index is greater than 70%, or when the void ratio is less than 0.55. So when we observe the load settlement curve, so it passes to a peak value and then drops down. So the peak value, from the peak value, we can find the ultimate load carrying capacity. Then second one is local shear failure. So this kind of failure occurs in sand or clay with a medium compaction. Here the failure pattern is clearly defined only below the footing, and the failure surfaces do not reach the ground surface. There is only slight bulging of soil adjacent to the footing. Failure is not sudden and there is no tilting of footing. So here ultimate bearing capacity is not well defined. This type of failure occurs when the phi value is less than 28 degrees, or when the density index is between 35 to 70%, and when the void ratio is greater than 0.75. So here there is no definite peak value for the load settlement curve. So we have to find the ultimate load based on either a single tangent method or a double tangent method. Then third one is punching shear failure. So here in this kind of failure, the failure pattern is not observed, and there is no tilting of footing and there is no bulging of soil around the footing. Failure is characterized in terms of very large settlements. The footing just shears into the soil to a great depth. Ultimate bearing capacity is not well defined, And this type of failure occurs when the density index is less than 35%. So here also when we observe the load settlement curve, there is no definite peak value, and it may be taken at a point beyond which there is a constant rate of penetration. Now, how to estimate the bearing capacity of soil? So there are various methods available to estimate the bearing capacity of soil. We can use the analytical equations like Terzaghi's method, IS-code method, Vesic method, Meyerhof, etc. And we can use the field tests also to estimate the bearing capacity, like standard penetration test, plate load test, etc. First, we will see the Terzaghi's method. So, in this method, the assumptions made are the soil is homogeneous, isotropic, and semi-infinite. The footing is long. The base of the footing is rough. The footing is laid at shallow depth, that is d value is less than v. The shear strength of soil above the base of the footing is neglected. The soil above the base is replaced by a uniform surcharge, gamma d. The shear strength of soil is governed by Moore-Coulomb equation. The failure is by general shear. So based on the assumptions, we can write the limitations also. Here only general shear failure is considered, and strip footing is taken, and this is applicable only for shallow foundations. For deep foundations, it is not applicable. Then in the Terzaghi's method, initially the equation is given without the shape factors and water table correction factors. But after modifications, the equation has become like CNC into SC plus gamma D and Q into RW1 plus 0.5 gamma B and gamma S gamma RW2. So in this equation, the first term is related to cohesion contribution, and second term is related to the soil strength above the base of the footing, and third term is related to the soil strength below the base of the footing up to a depth B below the base of the footing. So here C is the cohesion of the soil, NC, NQ, N gamma are the bearing capacity factors, which depends on the value of angle of shearing resistance, and SC, S gamma are called as shape factors, and these values are given in the table. So for different types of footings, the values of SA and S gamma are given. Then here in this equation, gamma is the unit weight of soil within the depth portion, and D and B are depth and width of the footing. RW1 and RW2 are called as water table correction factors. So by taking the shape factors into this equation, by substituting the shape factors SC and S gamma into this equation, we'll get equations for different shapes of footing. And these equations are related to general shear failure only. If it is local shear failure, that is when the phi value is less than 28 degrees, then we have to take effective parameters C dash and phi dash. That is, we have to take the C dash value as 2/3 C and phi dash value as 2/3 tan phi. Then we have to find the bearing capacity factors NC, NQ, N gamma corresponding to phi dash. So this in this case, in the local shear failure, we should represent the bearing capacity factors as NC dash, NQ dash, and N gamma dash. So whatever the table that is available for Terzaghi's method. So for different values of phi, we can find the bearing capacity factors from the table. So after finding the values from the table, we can substitute in the equation, and then we can estimate the ultimate bearing capacity. So here limitations are given. So based on the assumptions, we can write the limitations. Then effect of water table and bearing capacity. So here those water table correction factors which are there in the Terzaghi's equation. For that, the equations are given like this. RW1 equal to 0.5 into 1 plus ZW1 by D. So ZW1 is the depth of water table below the ground level. If it is within the depth portion and if it is at a depth of ZW1 below the ground level, then we can calculate the RW1 as 0.5 into 1 plus ZW1 by D. If the water table is located below the base of the footing at a depth of ZW2, then we can find the RW2 is 0.5 into 1 plus ZW2 by B. So suppose if the water table is at ground level, then the entire soil is submerged. The soil within the depth portion and the soil within the width portion is also submerged. So in this case, we should take the RW1 and RW2 as 0.5 and 0.5. That is because ZW1 and ZW2 will become 0. And if the water table is at the base of the footing here, then there is no effect of water table and the soil within the depth portion. So RW1 will become 1 and RW2, because it is submerged, it will be 0.5 because ZW2 will become 0.5. Then if the water table is at a depth of D plus B, see we have to consider the soil properties up to a depth of B below the base of the footing. So if it is beyond this depth, if the water table is beyond this depth, then there is no effect of water table on the bearing capacity. In that case, water table correction factors will become 1. If the water table is at a depth of ZW1 below the ground level, then RW1 value we can calculate using this equation, 0.5 into 1 plus ZW1 by D, and because the soil is submerged, RW2 can be taken as 0.5 because ZW2 will become 0. And if the water table is at a depth of ZW2 below the base of the footing, then there is no effect of water table on this soil. So RW1 will become 1 and RW2 will become 0.5 into 1 plus ZW2 by B. So here one problem is given. A strip footing 1.5 meter wide is supported on a soil with its base at a depth of 1.5 meter below the ground surface. The soil properties are C equal to 15 kPa, phi equal to 28 degrees, gamma equal to 18 kilonewton per meter cube and gamma dash equal to 10 kilonewton per meter cube. Determine the ultimate bearing capacity if the water table is at great depth, at the level of footing, at ground surface. NC, NQ and gamma values are given. So first we have to write the equation for strip footing by taking the shape factors as 1 and 1, SC as 1 and S gamma as 1. We will be getting the equation like this. And since it is subjected to local shear failure, that is based on the phi value, because here phi value is 28 degrees, the type of failure is local shear failure. So because it is subjected to local shear failure, we should take C dash in place of C and we should take NC dash, NQ dash and N gamma dash corresponding to phi dash. But here whatever the values are given, let us assume that these are corresponding to phi dash. Then if the water table is at great depth, first point is at great depth, then there is no effect of water table. So we can take the water table correction factors as 1 and 1. Then when we substitute in the equation, we should take 2/3 C in place of C. Then NC dash, whatever the value is given, that we should take it as NC dash, and SC is 1 because it is strip footing. Gamma D, here gamma value. So for the depth portion, as well as the width portion, we should take bulk unit weight only because here water table location is at great depth. So by taking the bulk unit weight and NC, NQ and gamma values which are given, we will be getting the ultimate bearing capacity as 1018.5 kilonewton per meter square. If thus in the second case, when the water table is at the level of footing, when it is at the base of the footing, then RW1 will become 1 but RW2 will become 0.5 because it is submerged. Then by taking submerged unit weight, by taking the RW2 value as 0.5 and saturated unit weight in the equation, when we take the water table correction factors, we should take the saturated unit weight. So saturated unit weight, to get saturated unit weight, we should add the unit weight of water to the submerged unit weight. Here submerged unit weight is given as 10 and the unit weight of water is 9.81. So we'll be getting the saturated unit weight as 19.81 kilonewton per meter cube. So by substituting the saturated unit weight in the third part of the equation and by taking RW2 as 0.5, we'll be getting the ultimate bearing capacity. Then in the third case, it is asked to find the ultimate bearing capacity when the water table is at ground surface. When the water table is at ground surface, both RW1 and RW2 will become 0.5 and we should take the saturated unit weights for both the terms, for both second and third terms. then we will be getting the ultimate bearing capacity. So here in this problem, square footing is given with width 1.5 meter, depth of the footing is 1 meter, and unit weight of soil is 17 kilonewton per meter cube. 5 value is given and its corresponding NC, NQ, N, values are given. Factor of safety is given. Water table is very deep. That means RW1 equal to 1 and RW2 equal to 1. Then we should find the percentage reduction in the say bearing capacity if the water table rises to the ground level. Initially it is very deep. Then we should calculate the value of bearing capacity. Then if the water table rises to the ground level, then RW1 and RW2 will become 0.5. In that case also we should estimate the say bearing capacity. So to estimate the say bearing capacity, first we should estimate the ultimate bearing capacity. And here also, since the phi value is less than 28 degrees, it is a case of local shear failure. So we should take C dash in place of C, that is 2/3 C, and we should take the NC dash, NQ dash, and gamma dash corresponding to phi dash. So whatever the values are given, let us assume these are corresponding to phi dash. Then after estimating the ultimate bearing capacity, then we should estimate the net ultimate bearing capacity, which is equal to ultimate bearing capacity minus effective overburden pressure. Then net say bearing capacity, which is equal to net ultimate bearing capacity divided by factor of safety. Then say bearing capacity equal to net say bearing capacity plus initial effective overburden pressure. So like this we'll be estimating the say bearing capacity. Then for the second case, when the water table is at the ground level, RW1 and RW2 will become 0.5, and we should take the saturated unit weight in both the places. So whatever the unit weight that is given, let us assume it is the saturated unit weight only. So because submerged unit weight is not given, we cannot calculate the saturated unit weight. So whatever the unit weight that is given in the problem, let us assume that this is only the saturated unit weight. So by taking the saturated unit weight in the equation, by taking the RW1 and RW2 values as 0.5, we can estimate the ultimate bearing capacity and then say bearing capacity using these equations. Then from both these values, we can calculate the percentage reduction, which is equal to 70.27 minus 35.13 divided by 70.27. So we'll be getting the percentage reduction in the say bearing capacity. Next example is, what is the ultimate bearing capacity of circular footing of 1 meter diameter resting on the surface of saturated clay of unconfined compressive strength of 100 kPa? What is the safe load if the factor of safety is 3? So here in this problem, the shape of the footing is circular footing. So for circular footing, the shape factors are 1.3 and 0.8. For circular footing it is 0.6. So 0.6 into 0.5 will be getting 0.3. So 1.3 CNC plus gamma D NQ RW1 plus 0.3 gamma B and gamma RW2. Here it is mentioned that it is resting on the surface of saturated clay. So it is resting on the surface. That means D equal to 0. So when D equal to 0, the second term will not be there. So the second term is 0. Then it is also mentioned that the soil is saturated clay. For saturated clay, we should know that the phi value is 0. And when the phi value is 0, the bearing capacity factors are NC equal to 5.7, NP equal to 1 and N gamma equal to 0. These values will not be provided in the exam. You have to remember. Okay, when the phi value equal to 0, the bearing capacity factors have to be remembered, and those values will not be provided in the exam. So we should take 5.7, NQ is 1 and N gamma equal to 0. Because N gamma equal to 0, even the third term will become 0. Second term is also 0 because depth is 0. Because it is placed on the surface, T equal to 0. So second term is not there. Because N gamma equal to 0, even the third term is not there. So QF equal to 1.3 CNC. And here C value is not given, but it is indirectly given in the form of unconfined compressive strength. So from this value we can find the cohesion, which is equal to unconfined compressive strength divided by 2. which is 50 kPa. So by substituting this value 50 kPa in this equation, QF equal to 1.3 CNC, NC value is 5.7, C value is 50 into 1.3. We will be getting the ultimate bearing capacity. Then we can calculate net ultimate bearing capacity, which is equal to the same value, because effective overburden pressure is 0. You will be getting the same value. This is 870 only, 870.5. Then net say bearing capacity equal to net ultimate bearing capacity divided by 3. So we'll be getting 870.5 divided by 3. This value is wrong. Then net say bearing capacity plus effective overburden pressure. Since effective overburden pressure is 0, we'll be getting the same value of safe bearing capacity. Then here it is asked what is the safe load. So safe bearing capacity multiplied by area of the footing. We have to multiply with the area of the footing, so that we will be getting the safe load. Another problem is a circular footing is required to support a total load of 900 kN at a depth of 1.5 meter below ground level. The soil has C equal to 20 kPa, phi equal to 20 degrees and gamma equal to 15 kN per meter cube. The water table is expected to rise up to the base of the footing in rainy season when saturated unit weight will be 18.31 kN per meter cube. Use a factor of safety of 2.5. Terrazagis bearing capacity factors 15, 6 and 3.5. So here, because it is circular footing, we should take the shape factors as 1.3 and 0.6. So that we will be getting the equation like this. And here pi value is less than 28 degrees. So this is the case of local shear failure. So we should take C dash in place of C, where C dash equal to 2/3 of C. And here it is expected to rise up to the base of the footing. That means water table is at the base of the footing. So RW1 will become 1 and RW2 will become 0.5. And when it is submerged, we should take the submerged unit weight, which is equal to saturated unit weight minus unit weight of water. And when we take the ultimate bearing capacity equation and when we substitute the values, we'll be getting the ultimate bearing capacity. So here total load is given. Total load is given as 900 kilonewton. So that is the safe load. So safe load divided by area, we'll be getting the safe bearing capacity. Safe load divided by area of the footing, because it is circular in shape, the area is pi by 4 d square. So we'll be getting the safe bearing capacity. So here d value is unknown. Here diameter of the footing is not given. So we should find the d value. So from the safe bearing capacity, we'll be getting the equation like this. Then from here also b value, b is nothing but d. So here also diameter is unknown. Then by equating these two, we'll be getting the QF value. After getting the QF value, we should find the QS value and then we should equate it to this QS. Then we can find the unknown d. Another example is, a column carries a load of 1000 kN. The soil is dry sand weighing 19 kN per meter cube and an angle of internal friction of 40 degrees. The Terrazagis bearing capacity factors are 15, 6 and 3.5. Find the size of first square footing if footing is placed at ground surface, and find the size of first square footing if it is placed at 1 meter below ground level with water table at ground level. Assume saturated unit weight of soil is 21 kN per meter cube. So first we should write the equation of square footing. Then in the first case, the footing is placed at ground surface. That means d equal to 0. So second term will not be there. Then by substituting the values, we can find the ultimate bearing capacity in terms of B. Then net ultimate bearing capacity in terms of B. Then safe bearing capacity in terms of B. Then whatever the safe load that is given, that is equal to safe bearing capacity multiplied by area. So safe bearing capacity is so much into area. When we equate it to 1000 kilonewton, we can calculate the value of B. And when we take d equal to 1 meter, we'll be getting a different equation, but the procedure is same. So by equating the say bearing capacity multiplied by area to the safe load, whatever is given 1000 kilonewton, will be getting the B value. Bearing capacity of footing subjected to eccentric load. Sometimes the footings will be subjected to eccentric load. So in that case, we have to reduce the length and width of the footing. So here effective width of the footing can be taken as B minus 2EB if the eccentricity in the width direction is EB. Then effective width equal to B minus 2 times of eccentricity in that direction. And if the eccentricity in the length direction is EL, then L dash equal to L minus 2EL. So after finding this effective dimensions of the footing, then we have to find the effective area, which is equal to B dash into L dash. Then we can find the ultimate load, which is equal to QF into L dash into B dash. So while finding the ultimate bearing capacity, in the third term, we have to substitute the value of effective width in place of width B. In place of B, we have to write B dash. Then factor of safety we can find by taking the ratio of ultimate load by load provided. So here because it is eccentrically loaded, on one side the load will be more, the pressure will be more compared to the other side. So here the uplift pressure varies. So on the side of eccentricity, it will be subjected to more pressure, more contact pressure compared to the other side. So we'll be getting two pressures, two contact pressures, maximum and minimum contact pressures. Maximum contact pressure equal to Q by BL into 1 plus 6E by B, and minimum contact pressure equal to Q by BL into 1 minus 6E by B. So here if the eccentricity is in the length direction, then we should take L in place of B, and this maximum pressure should not be greater than say bearing capacity, and minimum pressure should not be it should be greater than 0. Next method is IS code method. So in the IS code method, the equation is given like this. Here additional parameters are there, which are called as the depth correction factors and inclination factors. So DC, DQ, D gamma are called as depth correction factors, and IC, IQ, I gamma are called as inclination factors. When we observe the Terzaghi's method and IS code method, here additional parameters are there, and here shape factor is given for the surcharge term also, that is for the second term also it is given, and here in place of ultimate bearing capacity, net ultimate bearing capacity is there. The equation is given for net ultimate bearing capacity. That is the reason it is taken as -1. So here in place of gamma D, sigma dash is taken, and here water table correction factors are not there, but here this is the water table correction factor which is given only for the third term, and second term, because it is already effective pressure, here water table correction factor is not required. If it is submerged soil, then we can take the submerged unit weight to calculate the value of sigma dash. So here the shape factors are given with respect to different shapes of footing, and here W dash value we should take as 1 if the water table is at a depth below D plus B. If it is well below the base of the footing, then we should take it as 1. If it is at the base of the footing, then we should take it as 0.5. If it is intermediate, then we can use the interpolation method to estimate the water table correction factor W dash. So here these equations need not be remembered. These values will be provided in the exam. So only we have to remember the depth correction factors and inclination factor equations. So depth correction factor DC is given as 1 plus 0.2 d by b root n phi. N phi is nothing but pressure coefficient, which is equal to tan square 45 plus 5 by 2. And dq d gamma values are 1 when the phi value is less than 10 degrees. And if it is greater than 10 degrees, we should take it as 1 plus 0.1 d by b square root of n phi. And this inclination factors, when the load is inclined and when the angle made by this inclined load with the vertical is alpha, then we can calculate the IC and IQ values as 1 minus alpha by 90 square and I gamma equal to 1 minus alpha by 5 square. So here alpha is the inclination of the load to the vertical. And this is for the case of general shear failure. And for local shear failure, we should take the NC, NQ, and gamma values corresponding to phi m, where phi m equal to tan inverse 2/3 of tan phi. And we should take the C dash value in place of C, where C dash equal to 2/3 of C, like Teresa's method only. But table will be different. The bearing capacity factors are different. And there is one example. Calculate the safe bearing capacity of the soil for a rectangular footing 1.5 meter by 2 meter located at a depth of 1.4 meter in a soil whose properties are as given below. C equal to 0, phi equal to 25, gamma equal to 17 kN per meter cube. The water table is at the base of the footing. Take factor of safety as 2. Use IS code method. NC, NQ, and gamma values are given. So this is the equation for net ultimate bearing capacity. And here the shape of the footing is rectangular footing. So shape factors are 1 plus 0.2 B by L and 1 minus 0.4 B by L. So here since it is erosionless soil, because the soil is given as erosionless soil, we can ignore this first term. First term will not be there. So we need not calculate DC value, IC value and all. So directly we can take this sigma dash, also written as Q naught dash, which is equal to initial effective overburden pressure. That is the pressure at the base of the footing. So depth of the footing is 1.4 meter and unit weight of soil is 17. So I'll be getting the initial effective overburden pressure is 23.8. And shape factors SQ, S gamma we can calculate based on the dimensions. And dq, d gamma values using the equation. And we'll be getting the value. Then by substituting all these values in the equation, we can calculate the net ultimate bearing capacity and then net safe bearing capacity, which is equal to net ultimate bearing capacity divided by factor of safety. Then safe bearing capacity equal to net safe bearing capacity plus initial effective overburden pressure, that is 23.8. So here the water table is at the base of the footing. Since it is at the base of the footing, W dash equal to 0.5. And another example is a square footing of sides 2 meter is designed at a depth of 1.5 meter below ground level to support a total load of 1000 kN. The soil has C equal to 15 kPa, phi equal to 28 degrees and gamma equal to 16 kN per meter cube. Check whether the foundation is safe or not using IS code formula. If the factor of safety required is to take NC equal to 14.8, NQ equal to 6.4 and N gamma equal to 5.4. So this is also the local shear failure case where we have to find the C dash and phi dash values, which is equal to 2/3 C and tan inverse 2/3 of tan phi. So I'll be getting the values. Then we have to take the equation of net ultimate bearing capacity. So here when we substitute the values, we'll be getting the net ultimate bearing capacity, then safe bearing capacity. Then we have to find the net safe bearing capacity, which is equal to net ultimate bearing capacity divided by factor of safety. Then we should find the safe bearing capacity, which is equal to net safe bearing capacity plus initial effective overburden pressure. So we'll be getting the safe bearing capacity, and then when we multiply with the area of the footing, we'll be getting the safe load. So this value is the safe load. Here whatever the load that is applied on the footing is 1000 kN. So since the capacity is greater than 1000 kN, the footing is safe.